In this video, you'll see how the 3D Experience platform was used to create the system engineering on a coffee machine. John is the system architect for the project and created a dashboard in the 3D Experience platform using the 3D Dashboard app. Then, he gathered and linked various system artifacts created by different disciplines with the Systems Traceability Dashboarding app. He also used the Traceable Requirements Management widget to display the different types of requirements defined at the various stages of the project. This dashboard gives a holistic view of the overall coffee machine development, from the system studies to the design and implementation. He and his team have structured the activities and the data of the project based on the Cyber Magic Grid methodology developed at Dassault Systèmes. The Systems Traceability Dashboarding widget contains the tree that is used to select and link various objects from the 3D Experience platform and any external data. John used some scopes which include a particular set of data to be used by the project teams so they don't have to search for it. The team used this scope to analyze the data set and to preview the content of the models, create traceability links, and also review the content. The first step is to define what the system has to accomplish for the stakeholders. It starts with the elicitation of stakeholder needs. David is the requirements engineer. He has captured the stakeholder needs in the Traceable Requirements Management app. These include regulatory requirements, policy requirements, and marketing requirements. They also include requirements coming from various life cycle phases of the system, such as manufacturing delivery, maintenance, and retirements. These are essential to develop a sustainable system. All the stakeholder requirements will be further refined into technical system requirements by the system engineer, John. Here, David has collected the requirements such as the coffee needs to be freshly ground and the coffee needs to be affordable. The Traceable Requirements Management consists of two widgets. The Requirements Specification Editor allows you to author the requirement details. On the other hand, the Requirements Structure Editor allows you to quickly navigate and edit the structure of the specification folders and requirement specifications. The next stage is to understand the operational context of the system. Here we consider the system as a black box. It means that we see the system from the outside and define what's expected from it. As a system architect, John needs to create the architecture using the Magic Cyber System Engineering app based on SysML language. The system architecture is accessible in the 3D Experience platform in a web browser for collaboration. The browser allows us to access the 3D Experience platform data as well as the system architecture data from the Magic Cyber System Engineering app. Now we'll launch the Magic Cyber System Engineering app to see more details. Let's explore the various diagrams in the grid. First, John identified the life cycle phases of the system. These include phases like operational and maintenance. The life cycle phases help to identify all stakeholders that have an interest in the system. The goal is to elicit the needs and constraints of these stakeholders right from the beginning so that the design system is manufacturable, usable, and maintainable. Next, John identified the stakeholders such as the concept engineer, the development engineer, and so on. He traced the stakeholder with life cycle phases. For example, the development engineer is allocated to the development stage. According to the expectations of the stakeholders, the requirements can be updated. This is an iterative process. John created some use cases where he describes the interaction of the stakeholders with the system. Here in the operational phase, the coffee consumer and the power supply are interacting with the deliver coffee use case. He refined each use case to develop the black box functions, also called system services. Next, he defined the system context for the coffee machine with the help of the use cases. It captures all interactions of the system with its environment. Here, we can define the external interfaces of the systems with other systems. For example, the coffee machine is interfaced with the water and power supply systems. The next step is to define the key parametric targets of the system, called measure of effectiveness. Here, John included parameters such as the cost of acquisition, the mass, and the time required to serve the coffee. At this stage, he has identified the system interfaces and the system services delivered to the stakeholders and the measure of effectiveness. This completes the first level of the problem definition. Now the focus is inside of the system, also called the white box. The goal is to define a system specification for the solution to be developed. In order to manage the complexity, John decomposed the system into smaller systems. The system decomposition into subsystem is formalized under a block definition diagram. John has also done the functional analysis. He decomposed the elementary system services into a set of functions. Then, he allocates them to the subsystems. He also defined the flows between the functions. The resulting system architecture is formalized under the internal block diagram. From this system architecture, he defined the system requirements and their associated parameters, and defined the system specification, which consists of the functions, the functional interfaces, the subsystems, and the system requirements. This system specification is an input to the design of the solution. The next step is to define the working of the system to fulfill the system specifications. John has identified the system requirements. They are defined using the system analysis and are available for use across the enterprise. Next, Emily, a solution architect, has the responsibility to detail the architecture of the relevant components. She details the architecture to show the connections between the components. Let's launch the platform and open the data. Emily used the Functional and Logical Design app to capture a detailed behavior of every component defining its actions. She created the complete logical architecture of the system and created the behavior of each subsystem using the Daimoler Behavior Modeling app. Here you can see the behavior model of the power supply subsystem. Now you can simulate the behavior of the model. Here we will select cappuccino and study the change in the temperature using the graph. Notice that the temperature rises to a maximum of 85 degrees Celsius. Later, it drops and settles around 75 degrees. This is when the coffee is served. At this stage, the solution is defined. The temperature of the coffee is within the required limits. John has assessed the compliance of the solution against the system requirements. Now it's time to define the building of the system. Next, Jane, the design engineer, has derived the physical requirements and design constraints for every identified component by analyzing the solution architecture. She used requirements such as the number of cups the machine needs to hold and the overall dimensions of the machine. The final step is to implement this system. Jane used the physical requirements to design the physical system using 3D modeling apps. She then creates the simulation to virtually verify and validate the behavior of the system against the system specification. Let's see the simulation. She also reused a legacy controller to control the functioning of the system. At this stage, implementation of the coffee machine system is complete. John has also created a coverage matrix to study the traceability of the system. Using this view, he can analyze the impact of the related elements on the selected object. Here we can see that if we modify the serving assembly, we can have a cross-discipline impact analysis up to the stakeholders' needs. In this case study, we have seen how the CyberMagic Grid methodology helps to design complex solutions using system engineering. It's useful to track the entire project efficiently. It helps maintain consistency between the different engineering disciplines. It also helps to simulate the designed model and predict any impacts on the entire system.